Have you ever noticed how railway tracks have small gaps between sections, or how concrete sidewalks are laid with expansion joints? These deliberate breaks are there for a very good reason, to prevent materials from buckling or cracking when temperatures change. Just like these human-made structures, rocks in nature also react to shifts in temperature. Rocks primarily expand when they are heated and contract when they cool down due to the fundamental properties of their constituent minerals. This process, known as thermal expansion and contraction, is a significant factor in the physical weathering of Earth's surface. At its core, this phenomenon is driven by the kinetic energy of the atoms within the rock's minerals. Rocks are composed of various minerals, each made up of atoms bonded together in a specific crystalline structure. When heat energy is absorbed, the atoms within these minerals begin to vibrate more vigorously. This increased vibrational energy causes the average distance between the atoms to increase, leading to an overall increase in the minerals, and thus the rock's volume, which we observe as expansion. Conversely, when the rock loses heat and cools, the atomic vibrations lessen, the atoms move closer together, and the rock's volume decreases, causing it to contract. The extent of this thermal expansion and contraction varies significantly based on several key factors. First, different minerals have distinct coefficients of thermal expansion, meaning some expand and contract more than others for the same temperature change. For example, quartz expands significantly more than some feldspars. Second, the crystal structure of the minerals plays a role. Anisotropic minerals, which expand differently along various crystallographic axes, can induce internal stresses within the rock. Third, the magnitude and frequency of temperature fluctuations are crucial. Desert environments with large diurnal or daily temperature swings experience more pronounced thermal stress. Finally, the rock's texture, whether it is coarse-grained or fine-grained, impacts how these internal stresses accumulate and are released. Understanding the thermal properties of rocks is vital not just for geologists studying weathering, but also for engineers designing structures that interact with rock formations, such as tunnels or foundations. It helps explain features like exfoliation, where sheets of rock peel away from the main mass, often seen on large rock domes. This process is particularly pronounced in areas with significant temperature variations, where repeated cycles of expansion and contraction weaken the bonds between mineral grains and layers, leading to macroscopic fracturing. So, the continuous dance of heating and cooling causes rocks to subtly change their size, ultimately contributing to the gradual breakdown of larger rock masses into smaller fragments. This relentless, invisible work of thermal stress is a powerful force in shaping landscapes, transforming mountains into sand, and perpetually renewing the Earth's surface through the slow, steady process of physical weathering.